Hello, everybody. Yeah, this is our fourth episode, and all the other three episodes were linked with product development, innovation, prototype development, digital manufacturing, etc. So, today I would like to discuss more about the application of computer simulations in structural engineering, I mean, civil engineering. So, about 2 decades back, in the early 90s, every civil engineer had to go through a very complex process of performing hand calculations using mathematical analogy and arrive at results having gone through a lot of complex processes. Though in the early 80s, there were a lot of research conducted specifically in the areas of mathematical formulations in order to enhance engineering applications through simulations. So, very early, in the early, say about 1940s, 30s, and 40s, there were many professors who had come out with various mathematical concepts through which many engineering applications could be simplified. The calculations involved in many engineering applications could be simplified using computer graphics, computer simulations. So we had structural engineering tools, we had computer aided engineering tools, uh, specifically focusing on finite elements, which eventually we named it as or termed it as computer aided engineering. So we had a specific tool and we also had a general purpose tool. So the general purpose tools were Nastran, Answers, etc. So which had Fortran and Visual Fortran programming behind that. So today we call it as coding or codes, and earlier we termed it as programming. And then C, C++, Visual C++, and many other programming languages were involved in making these kind of engineering tools. So Professor O.C. Zinkiewicz had written or had published a book called Finite Element Methods. So that had been a universal book of reference. Many engineers had put their mind and interest in trying to understand every engineering structure, how it behaved. So that is when more of engineering aspects of a material were studied, whether the structure used to be a metal or a non-metal. So the kind of complex engineering process involved in the engineering of those materials had also been taken into account. So we had metals, non-metals, so linear uh, materials, non-linear materials, hyperelastic materials, viscoelastic materials, viscoplastic materials. So these are all several processes that a material had to go through eventually on the application of loads. The loads were of every kind. There were dead loads, there were live loads, there were rolling loads, there were braking loads, traction loads, dynamic loads, earthquake loads, so seismic loads, aerodynamic loads. So many type of loads were influencing on a structure. Say, for example, in civil engineering, we had we had a lot of structures, say specifically buildings, multi-story structures, dams, uh, bunkers, silos, chutes, cooling towers, etc., dams. So most of these structures uh, had different kinds of load and applications. Say, for example, a multi-story structure which was, which were more than 6 or 7 floors. These structures had to be uh, checked for various loadings. So one used to be the dead load on each floor. Then we had live loads, so people moving around and operating machines. So those were live loads, and we had rolling loads. So anything which any object or anything which had to move from one point to the other point. So that was considered as a influential load or a rolling load. And apart from that, the structure constructed on a specific region, okay, had to go through an external loadings. So that there used to be influence of air pressure. So at the ground, it used to be zero, and eventually it kept on increasing as the height of the building increased, and then the building had to be, assessed. It was influential on moments, rotations, etc. So all these civil engineering applications, structural engineering applications, geotechnical engineering applications, coastal hydraulic applications, marine structures applications, etc., had a lot of complex mechanics involved. And in order to reduce the complexity of these mechanical structures or civil structures, the universal mathematical tool which they standardized were called the general purpose finite element tools. So NASTRAN, called as NASA translation, was a general purpose code which was developed in NASA, National Aeronautics and Space Administration, in the early 1960s and 50s. So this specific code was written for specifically for aerospace structures, specifically on aircraft structures, rockets, satellites, etc. So this particular code was written, and it was given a graphical user interface where a certain set of preparations on the structure was performed, which was called pre-processing. And using several codes, languages, there were some codings done or programmings done, and these programmings had complex mathematics behind it. Your Fourier transform, partial differential equations, uh, matrices and determinants, etc. So all these complex mathematics were involved in that, and the structure was converted into finite and infinite systems. And these finite systems had several degrees of equations. It used to be monomial functions. There used to be binomial functions. There used to be polynomial functions. Uh, it had one unknown, two unknowns, three unknowns. Okay, and it had dependent and independent variables, several components were there. And instead of these equations were solved simultaneously and derived. A result was derived, and the derived results were used for post processing. Say, for example, any structure which was uh, fixed at one end and there was a load application on the other end. Okay, there was a deflection and there was a moment and there was a rotation being a cantilever, and the maximum deflection had to be evaluated, the maximum stress had to be evaluated. Okay, so this particular structure had to be simplified into a one-dimensional entity. We generally called it as either rod or beam or bar, and on the application of a point load onto that, there was a deflection, there was a rotation, and because of the rotation, there was a moment created, and then there was a stress. And all these things were calculated using the Euler's equation. So this was the usual procedure, and this procedure had to be converted into mathematical analogy, and it was coded, and then a particular system was derived at, and this system was called as the general purpose software. Okay, so now whatever results were arrived at or evaluated, that had to be seen, it had to be visualized. So we had a specific part of that particular software called post processing. So first we have a preprocessor, then we have a solver, and then we have a post processor. So the preprocessor is the ones which will completely create a meaning for that particular structure. That is the with your loads, boundary conditions, constraints, and then all the material properties, etc. So any structure, we know that any structure, when we apply a certain load onto that, that is subjected to deflection, and because of the deflection, there used to be a stress developed, and this deflection used to be of a certain factor delta, and then this delta used to be dependent on the specific length of that particular object or a structure. Okay, and it also dependent on the depth, the width, or the radius of that particular uh, structure. So now, since there used to be a length, width, breadth, radius, etc. involved, this particular structure was subjected to a direct stress, it was subjected to a combined stress, it was subjected to a bending stress. So the direct stress and bending stress combined together is called as the combined stress, and all these three stresses put together is what we call as von Mises stress. So this is the general stress strain theory. So now for any structure made of a specific material, okay, on the application of a load, there is a increase in strain. The strain increases to a certain extent, and then from that point it starts yielding out. And once it starts yielding out, okay, the material properties could be retained at certain point, and from there beyond a certain point, on further application of a load on a certain factor, this elongation increases. And once this elongation increases from that particular point, it cannot be reversed. To certain point, it can be reversed. So the point till which it could be reversed, we call it as hyperelastic, and the point from where it can no more be reversed is called viscoplastic or viscoelastic. So that's the zone from where the material elongation cannot be reversed back. So these are all the strain theories. It all depended on the material properties. Okay, it depended on the geometrical configuration. So when there is an influence on the geometry, we call it as geometrical linearity and non-linearity. Okay, and when it is influential on a material, we call it as a material linearity and the material non-linearity. And why we call it as a material linearity and non-linearity is simply because at some specific point when the stress and strain is proportionate and then that can be reversed. Okay, we call it as linear material. Beyond that specific factor, once your the deformation increases, it cannot be reversed. That is where the material cannot get back its normalities. So that is what we call as material nonlinearity. So this specific software developed by NASA, which is called Nastran, found immense application in aerospace structures. And similar to that, there used to be a company called ANSYS, and this company ANSYS generated a general purpose software. Okay, with the similar kind of coding procedures, programming languages, and they developed a preprocessor, a post processor, and a solver. Okay, and this was a heavily or extensively used by turbo machinery, heavy structures, oil and gas industries, etc. Now, as time passed, okay, because most of these softwares were very complex until and otherwise the engineer had a good knowledge about both mathematics, that is the numerical methods, and at the same time the material physics or the mechanics. Okay, the engineer was not able to use the application. So later on, there came a system where the companies that worked on these specific tools understood that there is a need for a computer aided designing or a drafting tool which can eventually reduce the complexity of their system. And that is how companies like Dassault System uh, and SolidWorks, etc., they developed their own tools. So SolidWorks came individually as a software company from the United States, and they developed the software called SolidWorks. And a company called Dassault System, a part of the Dassault Aviation from France, they developed a software called CATIA, Computer-Aided Three-Dimensional Integrated Application, CATIA. And this CATIA was extensively used for aerospace application. So the Dassault Aviation Group, in fact, were pioneers, veterans in aerospace engineering, and they are the creators of the aircraft called Falcon, the Dassault Falcon, and for most of their styling, designing, activities, simulation activities, they used this particular software called CATIA. And eventually, the software company called SolidWorks Incorporated that merged with the Dassault system, and today it is a single company called Dassault Systems (DS), okay, which has both SolidWorks and CATIA in their platform. Okay. So what has happened is eventually, on the formulations of CAD tools and making it more intuitive, all these systems again got combined together. The CAD, the computer-aided designing part, the computer-aided engineering part, okay, combined together, okay, and this became a design validation. Okay, similarly, parallelly, I can say parallelly, there used to be a certain platform called computer-aided manufacturing, where the companies developed computer-aided manufacturing tools, so specifically for their process integrations and specifically for all the processes involved in manufacturing. Say you have machining, you have turning, you have milling. So all these applications were digitally put inside the CAD interface. Okay, and the manufacturing process which happened in the shop floor were completely replicated in the virtual environment through the CAM softwares. So we had CAM separate, we had CAD separate, and CAE separate earlier. So there was a specific team, a product development team that focused only on the CAD tools, and then there used to be a manufacturing, digital manufacturing group that was involved only into CAM applications, and there was a product engineering group or a product validation group where they were day in and day out involved only in solving these systems to apply loads, boundary conditions, or the physical parameters or any physics into it, and then solve and find out whether the system used to be stable or unstable. So three different teams were operating earlier, and all these teams had to correlate their results one another, and only with that correlation they were able to conclude on a specific design of the software, of that particular product. And then the final product drawings, the engineering drawings, were released to the shop floor, from where the manufacturing of that particular product happens. And now there used to be a department for continuous improvement, which was focusing on only improving the product or optimizing the product in every way. So sometimes the material, the product used to be heavily designed. Okay, and those products which were heavily designed had to be again, optimized for material, for geometrical, volumetric efficiencies, etc. So, as I mentioned earlier in the last two, three episodes, where the complete product life cycle of a product involved conceptualizing, product design, then product prototype development, and then from there testing and measurements, and then from there digital manufacturing, and from there again your manufacturing, and then you had your production. So all put together is what we call as a product life cycle. Okay, so any product from the concept to the production to the market involved all these phases combined. Okay, so now let me come back to the subject, the application, which is in the civil engineering industry. So the last time I discussed about a certain aspect about impeller, the induced draft fan impeller, which was used in cooling towers. So cooling tower is a civil structural, engineering subject, or a what do you call structure. Okay, where there is a specific application where it has to remove hot air and all the other noxious air from the ground level, swirl it, and push it to the upper atmosphere. So this used to be the purpose of a impeller. And this particular impeller were earlier designed many, through the processes. You had cyclic symmetry, then you had axis symmetry. So those were all simple design concepts through which any structure could be simplified. Okay, any most of the cyclically symmetrical structures could be either taken as axisymmetric or plane strain or plane stress. Okay, and then we find out, arrive at a result. Okay, so it's basically to understand the hoop stress involved inside the vessel. Okay, or your circumferential velocities, rotational velocities, and the other parameters like deflections, etc. Okay, but when these structures were subjected to complex loading, say for example, you have a turbine, and this turbine has got a central shaft, a shroud, okay, and then it is connected to a shaft, okay, and this shroud is again connected with the other members, okay, your top plates, the bottom plates, the top blades, the stiffeners, the bottom stiffeners, etc. Okay, all these had, the structures had its own specific purposes. Okay, so when it rotated at say about 1000 rpm, okay, there is a circumferential, hoop stress which is involved, or a tangential, the velocity which is involved, and because of its continuous swirling, it picks up or it swipes the air from the bottom region and pushes it to the top region. So this is the actual physics involved. Okay, and this particular structure, when designed, it has to be considered, it has to be checked for various factors. Your deflections, your von Mises stresses, okay, the stress developed between the shaft and the shroud, okay, and what should be the thickness of the shroud, what should be the thickness of the stiffeners, what should be the thickness of the blade, and what will be the actual profile of the blade. So lots and lots of physics, multi-physics is involved in this particular subject, especially impellers. Okay, and then there is a lot of dynamics also associated with it. Okay, because at some time t is equal to 0, it is at rest. At time t is equal to 10 seconds, the velocity increases, the rotational velocity increases, then slowly your rotational velocity comes down, then again it increases. So since there is a change in your force or dynamics with respect to a certain time, okay, this becomes a transient system, it becomes a dynamic system, and now all these dynamic systems will have a considerable amount of dynamic loadings or shock loadings on the structure. So from a static system, the structure has now become, it has taken a different shape, where there is a possibility for impact loads or traction forces or brake forces or bearing forces or even jerk loads. Okay, and now these are all loadings which will act on that particular structure for a certain period of time. There is an amplitude involved, isn't it? So now solving these equations further becomes very complex, and that is the reason we have planned to associate all, that is your design a product design tool with the product validation tool, so that every time you make some changes with the model, okay, and then you have a chance to rerun the solver, and once you rerun the solver, it will again take the new variables, the thickness, maybe the first iteration the thickness is about 6 mm, so that is failing, there is a huge deflection. So what happens is the second iteration, the system, uh, we say, let's go for 8 mm thickness. So on different iterations with different thicknesses of these members, we can simulate the results. And now at some iteration, the system becomes stable. The blade thickness, for some specific blade thickness, the deflection is nominal and the stresses are within permissible limits. So most of the structures we use cast steels or mild steel MS plates. Okay, so steel has got its own Young's modulus, Poisson's ratio, bulk density, and your expansion, thermal expansion coefficients, etc. So these are all the things which is considered, these are all the things which is considered for your system simulation. And now once the simulation is performed, you will get the results. Now different materials, different thicknesses or the geometrical parameters, the different results are all iterated and correlated. Okay, so the best results are taken. So what happens is, in order to reduce the time taken for all these processes, okay, we generally uh, assume a lot of things. So what we do is, a good designer will think, okay, whether this structure is going to be a plane strain structure or whether it's an axisymmetrical structure, or whether this particular structure is a bulk system where every component has got a different variable thickness, it could be thickness or it could be radius or whatever it is, and simultaneously when there is a change in two or three or more variables, then the surface model, the mid surface model of the system is considered, and variable thicknesses are applied by selecting that particular surfaces. Okay, and finally we conclude on a result, and once that result is achieved, then the thicknesses are assigned for the surface models. And once the thicknesses are assigned for the surface model, this becomes a full-fledged 3D model. And this 3D model, the full-fledged 3D model, is sent for manufacturing, designed for manufacturing, where the engineer considers the geometrical dimensionings and the tolerances. Say there could be components which will be fabricated. There could be some components which is casted. Okay, so depending upon the process, the manufacturing process, the GD&T is also considered. And finally, the drawings, the general arrangement drawings are all dispersed to the shop floor. And from that, the shop floor will start the manufacturing process. Okay, so this is the actual scenario behind the our this one application of the advantages of using computer simulation on any structures. So cooling tower is a civil structure, and today we discussed about how the impeller thickness, or how the impeller, the geometrical parameters of the impeller, the material parameters of the impeller is going to influence heavily on the system, the design of the system. So let us take a mechanical structure, a machine, okay, on our next episode, and I will explain you how the complete machine design is done, how the machine building is done, and what are all the kinds of loads which comes on that particular machine, okay, and how the optimization is done. Okay, so let's stop here, and I'm again trying to communicate with you one thing. If any of you have got any kind of doubts, or any kind of what do you call mental roadblocks, based on some what do you call assumptions or criterions, okay, which you feel is a bit difficult for you to understand, you please send me your query, and I will send you the explanations for that. Okay. Now, in order to make this more efficient and connected, I would request you to kindly subscribe this, and you will be able to get connected with my other videos also. Because this particular system, I'm not only focusing on computer-aided engineering, I am also going to focus on computational fluid dynamics. Okay, not only the structural part, I mean the fluid dynamic aspects also, and we will be dealing with many other complex engineering processes. Okay, so thank you very much.